Right, y'all. We're currently recording, and before we get started today, the first one thing that I want to mention is that um, we have an exam in a week. This will be our fifth chapter and last chapter in Module 1. Um, we've done 1, 2, 3, 8, and then this is 4. Um, of course, that um, Of course, that exam is going to be done using lockdown browser with webcam. So let me direct you again to this little spot here on the important info about the exams where you need to download that piece of software and have it ready for that exam. And one of the things that we're going to do this Thursday, one of the things we're going to do Thursday is we're going to look at your study guide for that. We're going to go over that study guide and review a bit. So today, what we're dealing with is extrusive igneous rocks. Looks like I am in the wrong part of the slideshow, so let's go all the way to the beginning. Okay, there's our lineup, our outline for today. So last week, intrusive igneous rocks. Intrusive igneous rocks are the result of cooling of molten rock underground. So obviously, hopefully, obviously, extrusive igneous rocks are going to be cooling a molten rock above the surface, so below ground. So let's look at our little clip art thing again, where we've got the grass showing the difference between below ground and above ground. And of course, while molten rock is below the surface of the earth, it's known as magma. And if magma stays below the surface of the earth and cools off into igneous rock, it is known as intrusive rock. And that's what we spend a lot of time on in chapter 3 for that. If that molten rock makes it above the surface of the earth, so usually through a crack or a hole in the ground, if it makes it up to the surface of the earth, now it is known as lava. So lava and magma are really not different from each other except for their location, except for where they exist. Otherwise, they can be made of exactly the same stuff. Lava is above the surface, magma is below the surface. Well, when lava cools, it will form extrusive rock, and that's the main difference. However, there is another way that molten rock comes out of the ground, and that's that it sometimes is oozed out of the ground like lava, but sometimes it's exploded out of the ground. If it is exploded out of the ground, we call that type of material pyroclastic material, which literally means it means fire fragments, fire broken. So broken by fire. But of course, when this happens, this material is also cooling above the surface. So it's still considered extrusive rock. You might wonder, why do we separate these so much? We've already determined that either one of these can be found above or below the surface, and that the only real difference is where they cool. Well, why is that so important? It's because the conditions down here are radically different from the conditions up here. So this leads to different cooling rates, and different cooling rates leads to different rock textures. So they don't look the same. They look really, really different. So where they cool leads to difference in cooling rates, which leads to differences in texture. And that's it kind of summed up, but of course we're going to look more closely than that. So here's a good example of a pyroclastic eruption. Not a whole lot of lava oozing out of the ground, running down the slopes of this volcano. Instead, most of the molten material is blown directly up into the atmosphere. So this is considered pyroclastic material. That is the 1980 eruption of Mount St. Helens. So let's talk a little bit about, do these eruptions well, let me back up a little bit. The process the process of molten rock leaving the ground, either one of these two methods, the process of molten rock leaving the ground is known as volcanism. Volcanism is molten rock leaving the ground. So, does volcanism affect people? Volcanism has had a profound effect on people. It is responsible for some of our atmosphere composition. It's responsible for contributing water to our oceans. It builds up land. There are several island chains that have millions of people living on them that wouldn't exist if not for volcanism. It can lead to a lot of, if you have a really large eruption of this style, this can refract sunlight, which can lead to temporary cooling and also spectacular sunsets. So the main effect on us, though, is when we think of volcanism, is the destructive nature of volcanoes. So in the background of this photo, you have Mount Vesuvius, and Mount Vesuvius is famous for having buried the towns of Pompeii and Herculaneum. We know that this happened because there are written accounts from the people that were around then. Um, there were written accounts of this happening. Let me check and see if I need to let someone in the meeting. Looks like perhaps they've already been let in. Anyway, let's go back to the slide. There are written accounts of this, uh, and the cities were so completely buried that the tale of the burial of those cities started to take on more of a myth and legend because no one could ever find the cities. That's because they were buried under 5 to 8 meters of ash. So it wasn't until 1,500 years later or so that they actually located the remains of that. So that's the area was buried so quickly that people's outlines of their body were preserved in the ash that fell in these gruesome death positions. So another thing that we study about volcanism, is the destruction that it occurs. In fact, the destruction that it causes. And in fact, that's going to be the first thing that we look at, because not all volcanoes erupt in what we would call an explosive manner. If we go all the way back to that first graphic here, some volcanoes ooze lava out of the ground, some of them exploded out of the ground, and some will do both depending on what day it is. Rarely do you have a volcano that's doing both of these at once. If you've got an explosive eruption, most of the stuff is coming out into the atmosphere. But if you've got a non-explosive eruption, most of the stuff is oozing out onto the ground. So we actually have a different name than non-explosive for those types of eruptions. So let's get back over to here. Typical explosive eruption looks like this. Mount St. Helens, May 1980. Also, I have this video right here of an explosive eruption in New Guinea, Indonesia, or actually, no, New Guinea it borders Indonesia. It's not actually Indonesia. All these videos I'm going to show you today, I have posted on in Module 1 in a place called Volcano Videos. And this is Mount Taverver. I guess that's how we're going to pronounce that. And crater is a little bit hidden behind the landform there. But they were filming this. They apparently had some idea that something might be happening soon. And they were filming it. So keep in mind, this is an explosive eruption, but the magnitude of it is not great. Although it is explosive, it's not hugely explosive. So I'm going to forward block because nothing really happens for me. I think they see a little bit of steam coming up, but nothing has really happened yet. But I promise you it's going to happen. This video runs out. And just like that, all of a sudden. So yes, that's an explosive eruption. We see large chunks of debris that soon could be. And then the whole boat was shaken by that. You can kind of see the camera. I don't believe the sound is on, although let's go ahead and make that part available so that we can hear the shock wave. Okay. Now we should be able to hear. I want you to watch for a couple things here. Watch for the shock wave going up into the clouds, but also running down the slopes of the volcano. And then after several seconds, the shock wave is going to hit.
Here we go.
So
Wait till we get the boat.
and there it was,
Wait till we get the boat.
getting to the boat. And of course, you can see the splashes. So yes, this is an explosive eruption, although we would not consider this a high magnitude explosive eruption. Something like St. Helens here, it dwarfs that. And then there are others that have dwarfed the 1980 eruption of St. Helens. So that's fairly small potatoes as far as explosive eruptions go. What you're looking at here is the lava flow from a non-explosive eruption, where instead of the stuff being blown into the atmosphere, most of it is flowing onto the ground. Now, admittedly, there is a little bit of stuff getting blown up into the air, but as you can probably see, this is not being blown near as high as the stuff in that last video, and it's all falling down pretty quickly. In fact, some of it has already started to cool off and harden into rock. So this is a non-explosive eruption, or as we like to call it, effusive. And that's effusive with an E. So effusive eruption is non-explosive. And so I've got the pictures of the two here. And on the left, we've got an explosive eruption photo, and on the right, we've got an effusive eruption. So what we want to be able to do is it possible to predict whether an upcoming eruption is going to be explosive or effusive? In other words, what determines whether or not a volcano is going to explode? I'm sorry, whether a volcano will erupt this way or will erupt in that style. And it turns out there are several different things that affect a volcano's behavior, its eruptive behavior. But the main one is the viscosity of the magma itself, the viscosity of the molten material, which is more or less meaning the thickness of the molten rock. Viscosity, by definition, means resistance to flow. So something with high viscosity is really resistant to flow and is thick and flows slowly. And so that'd be something like peanut butter is something I like to think of. Peanut butter is very viscous and thick and flows really slow. Something like water and blood, those are things with low viscosity. So how do those affect, how does the thickness of the lava affect the eruption? It's like this. All lavas have gases dissolved in them. These gases are dissolved in them much like the gases are dissolved in a Coke until you open it up. So you don't see those gases, but they're dissolved in there. As that lava comes closer to the surface, though, the pressure that's holding that gas in solution lessens and lessens. And so during the eruption, the gases are coming out of the lava. The gases are coming out of solution and escaping the lava. The question is, what is it easier for gases to escape from? Really, really thick lava or thin and runny lava? And the answer is, it's pretty hard for gases to escape from the thick, high viscosity magmas, which means that the pressures build up higher and higher and higher until eventually they must escape. So the pressure buildup, because of the stiffness and thickness of the lava, leads to explosive eruptions. Gases easily escape runny lavas. They escape before there's been a chance for high pressures to build up. So they simply tend to erupt in effusive manners. And there are other things that affect it, but we're mainly looking at viscosity right now. So you might think, okay, if we've got a low viscosity lava, then it's going to erupt in an effusive manner. That's what this is saying here. But if you can actually get a sample If you can actually get a sample of the lava, then it's probably too late. It probably has already erupted. So is there anything that can be used to predict viscosity? Is there anything that affects the viscosity of a lava? And yes, it turns out that amount of gas dissolved affects the viscosity. The temperature of the lava affects viscosity, but none of those affect it so much as the silica content. The silica content of the magma has a great deal of effect on viscosity. And it's a straightforward relationship because magmas with high silica content are thick. Magmas with high silica content are thick, and therefore they tend to erupt explosively. Magmas that are low in silica tend to have low viscosity, really by definition. Low silica magmas are runny, faster flowing, do not trap gas uh, for very long. Gas escapes before pressures can build up to explosive levels. Well, now we're getting into somewhat familiar territory because we have names for silica rich magmas and silica poor magmas. Those names, we've been trying to drill them into y'all's heads, but it is felsic and mafic. And we also know that mafic rocks tend to be dark color and felsic rocks tend to be light color. So let's just look at the color of these rocks that are hardening. As this magma hardens into rocks, it's making black rocks, and the dust that's being put out by this is much, much more light colored than, and even the materials on the side of the volcano, if I go back for a bit, um, these materials coming out are lighter in color. The materials that are dumped on the sides there are lighter in color. So it actually does all check out. Mafic lavas erupt effusively and cool into dark mafic rocks. Felsic lavas erupt explosively, usually explosively, and cool into lighter colored rocks. So one of the ways that we might predict eruptive style is look at the actual rocks that the volcano is made of. Volcano is made of black rocks. That means it probably erupted effusively in the past. If the volcano is made of lighter colored material, means it erupted explosively in the past, most likely. So what are some of these various things that come out of a volcano? We're going to look at five different things. Actually, we're going to look at four of these in depth, and we're going to push one of these, the lahar, to a later chapter because it has a little bit more application in that later chapter. So all volcanoes are emitting gases. Some of them toxic. Actually, most of them are toxic. So someone who's, and I mean, even that cloud looks kind of yellow, but don't breathe in a yellow cloud if you have a choice. Um, Volcanologists, of which this is one, volcanologists who hang out near the vent of a volcano where these gases are coming out, they do need to have protection. They need to have filter those toxic gases because there's things like hydrogen sulfide, carbon dioxide, sulfur dioxide, hydrochloric, hydrogen chloride gas. These all can be toxic. Another large component of volcanic gas is water vapor. So yes, there is usually a lot of steam involved. And if you see a cloud coming out of the volcano that is white, then that volcano is only putting out gas at that time. If it is darker, then it's got gas and solid materials. Um, Here's the thing about volcanic gases. They're toxic, but they are rarely a hazard to people because most people don't live right next to a volcanic vent. By the time these gases have traveled to populated areas, then they have become diluted, they have diffused in the surrounding air and dispersed and become diluted to non-toxic levels. Only the people who happen to be around the vent of an active volcano should be taking precautions for that. Okay, the second type of material, and of course, here we're calling it tephra. So before I get into what ash is, let's talk a little bit about tephra. Tephra is pyroclastic material. It is when the lava is blown into the atmosphere. When the lava is blown into the atmosphere, it might be in the form of large blobs, it might be in the form of small blobs, or it might be in the form of microscopic blobs. Seems like I said blogs for a second, but I mean blobs. Um, the large blobs, surprisingly, are not that dangerous. They're called volcanic bombs because the wind resistance turns them into a bomb shape as they fall to the ground. But they're not that dangerous because they rarely hit people. They are too large and heavy to go a long, long way from the volcanic vent where people live. Um, so volcanic bombs rarely fall on inhabited areas. If they were to fall on you, that would be business. That would be, that would be some heavy stuff, but they usually do not. Now, the next larger size is called cinders, and these are like golf ball size to pebble size, anywhere in between. And you've probably seen these cinders used as landscaping for banks and fast food restaurants, and you can get them in a bag at Lowe's called lava rock. People use them in their grills too, um, as a charcoal substitute. I guess a reusable charcoal substitute in a propane grill. Anyway, these are not that dangerous because they are smaller, and one hitting you on the head could make you mad. It may even give you a lump, but it's not likely to maim you or kill you. But these do have a farther reach because they're smaller. And that's the thing. An, an explosion that is big enough to send something a long way is also big enough to blow that blob into smaller pieces. So most volcanic eruptions simply do not send volcanic bombs miles and miles away. They they most of these large things fall close. The third size of material, though, can go all the way around the globe, and that is volcanic ash. Volcanic ash begins as microscopic lava droplets. This is the result of highly explosive eruptions. And any cloud coming up out of a volcano that is not white is containing ash. Ash is literally particles. So there's a misconception. Volcanologists do not like it when you say a volcano has smoke coming out. Um, Smoke, it's not smoke. It is gases and ash. It's literally this particulate matter. So with a really, really explosive eruption, the lava literally gets blown into smithereens. It gets blown into tiny droplets, even a mist. And so these droplets are so small that they cool almost as soon as they hit the atmosphere. So that instead of droplets, now they are actually particulate matter. They're solids, but they remain microscopic. So ash is tiny, tiny microscopic particles, but that makes them extremely light. It means that they can travel a long, long ways. The wind can carry them a long, long ways. Of the three types of tephra, the bombs, the cinders, and the ash, ash is by far the most hazardous. This is what ash looks like if you get a handful of it. It's pretty much dust. It's dust particle size. The problem comes when there is more than just a little bit of it. Because it is solid, it's really just tiny bits of rock. It's an eye irritant. It's a lung irritant. It can cover people's crops. It can mess up their water supply. It can affect visibility when you're driving. All these things. Um, Worse though, the biggest hazard from ash is structural collapse. Um, you notice that this building has what appears to be several feet of ash on there. That's a lot of weight to be asking a building to hold up, which was probably not built to hold up that much weight. So most deaths from ash fall are the result of building collapse, not people choking on them or anything like that, but structural collapse. So ash is hazardous, but it is not as hazardous as the next two things on the list, the pyroclastic flow and lahar. Together, these two are both pretty much tied with each other for the most deaths. So these are by far the most hazardous. So let's look at what a pyroclastic flow is. A pyroclastic flow is a mixture of gas and ash. We're going to take a quick look at one. Well, in a second, I'm going to look at a video of one. So it is a mixture of gas and ash. As you can see from this diagram, a lot of times a pyroclastic flow happens when you've got an ash cloud that's going up into the atmosphere, but part or all of that cloud simply becomes too heavy to stay buoyant from the heat of the eruption, and it will collapse. And now the whole mess is speeding down the slopes of the volcano. So this is like a really hot landslide, and that's exactly what it looks like. It looks like something from the movies. This is 7 minutes of pyroclastic flows. We're not going to watch 7 minutes, but that cloud that's running along the surface, hugging the surface, is a pyroclastic flow. The problem with that pyroclastic flow
walk across
is
in front of
that
the camera.
it's several hundred degrees Celsius inside of it. And it doesn't rise up into the atmosphere like the ash cloud does. It hugs the ground. So it's denser than air, it's really hot, and it may be traveling at more than 100 miles an hour. So these are extremely deadly because they are hot, fast, and dense. They hug the low areas. They incinerate anything in their path. Here is a photo of a little bit more deadly pyroclastic flow. I'm sorry, a video of one. Oh, this is just showing kind of the end of it. This one has no sound on it. There's pretty much no surviving a pyroclastic flow. If the cloud gets you, you're not surviving. And boy, they ended that just before it was going to show that cloud. I've seen a different version of this video, and that cloud is just fixing to peter out and start to drop right there. That's the one good thing about pyroclastic flows, is that they tend to exhaust themselves after about 10 to 20 kilometers, 10 to 15 kilometers of travel. So it generally only affects people that are that close to the vent, which includes volcanologists, but it also includes, there's actually a lot of people that live inside that hazard zone worldwide. This is Volcan Fuego. One of our students posted a video that I assume is extremely recent from this same volcano that showed a more effusive eruption, but from this eruption, it was doing an explosive one. You can see the pyroclastic flow down in this valley. It is denser, but eventually what happens is the pyroclastic flow from upslope continues to feed that, so that eventually this stuff winds up coming out of the valley. There. So that was really close. Usually you would probably get asphyxiated before you would burn. Not that that's any consolation, but extremely hazardous, dangerous volcanic phenomenon, right where those people were standing. Some more slides of these pyroclastic flows. I see 1, 2, 3. There's at least 3 pyroclastic flows happening on the slopes of that volcano. Here's the result of a pyroclastic flow. This is an island in the Caribbean Sea called Martinique, and the volcano was Mont Pelée. The town, I forget the name of the town, but it was 20,000 plus people. And as you can see, the the buildings were incinerated by a single pyroclastic flow. 20,000 plus people lived here. There were 2 survivors of this. At least one of them was because he had been thrown in jail the day before, and the jail is buried. It was kind of a dungeon, so it was buried so deep that none of that horrible stuff could get to him. Okay, going back a little bit here. The Lahar. Oh, come on, went back too far. Lahar. I'm going to mention that a lahar is a volcanic mud flow, but we're going to talk about lahar as a hazard in chapter 9. So not this module. We'll mention that lahars are triggered by most explosive eruptions. In fact, most explosive eruptions produce ash, pyroclastic flow, and lahar. But that's all that I'm going to talk about today for lahar. So let's get to lava. Let's get to 2 guys who do not seem too concerned about the lava. Is lava dangerous? I don't know. Is it destructive? Here's what would happen if you tossed garbage into a volcano. So obviously, lava is extremely destructive. Lava is extremely destructive. We can also show that through some time lapse here. Just about 3 years ago in Hawaii, someone left their car in a bad place. And so we see this lava is encroaching it. No one was in the car, but they left their car in a bad place. And of course, the car's on fire now. Lava destroys everything in its path. The question is, can you get out of its way? And the answer is almost always yes. You just have to be smarter than the lava. You have to resist the urge to hurl yourself into the lava, I guess. So these plants are done for. This road is completely destroyed. But these guys are not that concerned because they've been watching how fast it's going, and it's not going to suddenly surge and overcome them. So lava is not as dangerous as the rest simply because it does not travel as fast as a lahar or ashfall or pyroclastic flow, or even gas for that matter. Does not travel as fast as them. So we just have to be out of their way. But these things all will eventually solidify into volcanic rock, which we are going to study and identify according to their texture and their composition. So remember that so far we've been using texture as synonymous with grain size. We've been saying, what does texture mean? It means grain size. So thinking back to chapter 3, last week when we dealt with phaneritic rocks, in chapter 3, that was large grained, grains that are large enough to identify, technically larger than a millimeter across, but large grains. That's what happens when magma cools below the surface. This is because the conditions below the surface are high pressure and hot. The surrounding rocks, if the magma is making its way up through surrounding rocks and intruding them, those surrounding rocks might be almost as hot as the magma itself, which means they do a really good job of insulating that magma from cooling. Intrusive rocks, for this reason, because they're so insulated by the surrounding hot earth, they tend to cool really, really slowly. Now, cooling means going from molten rock to solid rock. And on an atomic level, what happens is the molecules, the atoms that make up that molten rock, as long as it's molten, they're moving around. By definition, a liquid has moving atoms, moving molecules, and solids do not. With a solid, the atoms are placed. They can vibrate, but they're not switching around, changing places and stuff. So With slow cooling, that gives a lot of time for the atoms to move around and accidentally come into contact with another atom that they like to bond with, or accidentally come into contact with a growing crystal form that they can insert themselves into. As a result of that, slow cooling leads to large grains. Slow cooling allows the grains time enough to grow large. Your lab book on page 39 has of this. Your textbook on page 56, which we have looked at in the past. And here would be a sketch of phaneuritic that's just supposed to show that it's all large, chunky grains. And here's a photo of phaneuritic texture. So we see some large black pieces, some large gray pieces, and some large pink pieces in there. So let's compare that to what's happening with extrusive rocks. Extrusive rocks are belched or oozed or exploded out onto the surface of the earth. There is no insulating earth anymore to help keep it warm. So if you have a magma that's 800 degrees Celsius and it is belched into the surroundings that is 30 degrees Celsius, that's a radically different environment. To that lava, that's a really cold environment. In other words, cooling happens really, really quick. Cooling happens quick with extrusive rocks. And this simply does not give the grains time enough to grow very big. It does not give them time enough to grow very big. We still have mineral grains. We still have crystal frameworks where atoms are bonded with each other, and there's still room for more atoms in there, but there's a lot less time. So those um, those minerals simply, they get solidified and atoms get frozen into place before they've had a chance to grow large grains. So extrusive rocks have a fine grained or small grained texture. And our name for that is aphanitic. That's short for aphaneuritic, which a lot of times in science, if you put the letter A at the front of a word, it means non. And that's exactly what they're saying. They're simply saying that this is non-phaneuritic or aphanitic. Fine grained, like an illustration in your lab book, page 39, or in your textbook, page 6. Compare the grains here to the grains here. These are both magnified the same amount. And so here the grains are that size and some are that size, but here the grains are either really, really small or too small for us to see without magnification. So aphanitic technically means less than a millimeter, but for us, we can just generally say it's fine grained, it's small grained. The different texture makes these look really different. Why are the textures different? Because they cooled at different rates. Why'd they cool at different rates? Because their surroundings are so different. So different surroundings lead to different cooling histories, which lead to different textures. As far as composition goes, the composition of extrusive rocks might be the same as that of an intrusive rock. Cooling history does not affect composition, it affects the texture. What affects composition is what the magma was made of to begin with, what was the rock that melted made of, how far up the partial melting scale did it go. That determines the composition. So here we have samples of 3 aphanitic rocks. Notice that for all 3 of these, you're really, really hard pressed to find any grains. Now, this one has a few larger grains, but do these occasional larger grains, do they make up a significant portion of that rock? They do not. Most of that rock is this background ground mass of microscopic grains. So there is a big difference in texture. The colors may be really similar. The composition may be really similar, but the textures are different. So our first extrusive texture is aphanitic. There are several more. So intrusive rocks pretty much have one texture, phaneuritic. Extrusive have several. And so we start with aphanitic, but another common igneous texture is glassy. This happens when the molten rock cools so rapidly that the minerals don't have time to form a crystal structure. Instead, the minerals are just frozen into place in a random distribution, and that forms no minerals. I might have said minerals, but I didn't mean. The atoms are randomly dispersed so that they do not form minerals. They just form volcanic glass. This is actually a better example, this second one. So volcanic glass will have what we call a conchoidal fracture. And that is this surface right here, these kind of concentric arcs. It's the way that glass tends to naturally break. So if you were going to be really pointy headed about your definitions, you'd say, well, technically obsidian, technically volcanic glass can't be a rock because it's technically not made of minerals. However, I think we can still get away with calling it a rock. It sure looks like a rock. It acts like a rock. It throws like a rock. It breaks like a rock. So volcanic glass can be considered a rock. Save that argument for grad school. But right now, none of us really care enough of whether we can, we're all okay with calling it a rock. Hey, here's a third texture. This texture is called porphyritic. It is where the rock has two distinct sizes to it, or I should say the grains are in two distinct sizes. In this one, we've got a lot of large white crystals in there, and then the background of these is a lot smaller material. This one's probably even better, where again, we've got large white crystals and then this pinkish or reddish background where we have trouble seeing individual grains because they're so small. Also, good example of a porphyritic texture, lab book page 40. Now, what this looks like zoomed way in. We're looking at a thin section under polarized light. We looked at one of those last weekend. Last week, we weren't doing geology in the weekend, were we? We looked at one of those last week when we were watching how the quartz changed color as it rotated. I mainly wanted to look at the grain size here. Here's a millimeter. So hopefully you realize that in real life, a millimeter is about that distance between my finger and thumb. It's like that. So now we're majorly zoomed in. A mineral that is about a millimeter wide and several millimeters long, that's visible. That's visible without magnification. So that's visible. This is, that probably is, that probably is. But what about the rest of these things? How many of these grains does it take to make up a millimeter? About 30 or 40? It's really hard to tell, but extremely unlikely that without magnification you would be able to see any of these grains. With this intense zoom in, we see that they are grains, but zoomed out to a normal hand sample, we wouldn't be able to see them. They're just simply too small to make out. So this is what porphyritic texture would look like. A few large grains in an aphanitic ground mass. As far as how a rock like this would form, how do we get that? It's two-stage cooling, and we'll talk more about that next week when we get into our igneous rock lab. Okay, one or two more textures, and for extrusive, and so this one's called vesicular. And the main characteristic that you can see about that rock is, if I told you to describe me what that is, you'd probably say it's full of holes. And that's what vesicles are. Vesicles are holes. So this texture is a vesicular texture, and it's common in extrusive rocks. Note the part of the rock that's not holes, this gray part, still does not have visible minerals. They're too small. So really, this is just another version of aphanitic. This is aphanitic with a lot of holes. Where'd the holes come from? The holes came from the gas that comes out of solution during eruption. Remember, those gases are kept in solution by the pressure of the overlying rock, but as that magma gets closer and closer to the surface, the pressure decreases, and that just like when you shake up a Coke and then open it, you're going to get an awful lot of gas come out of solution. That's what's happening here, except that those gases are coming out of solution at the same time that lava is cooling off. So the space that those gas bubbles took up is preserved. The gas itself is gone, but the space they took up is preserved. So vesicular texture simply is a result of a high gas content of the magma. It was cooling as the gases were coming out of solution. If you could flash freeze a Coke as soon as you opened it, you might get something similar. You might get a Coke popsicle that had an awful lot of holes in the popsicle. Excuse me. Now, some magmas, some lavas are thick enough that the gas pressure can whip it up into a froth so that there's actually more air bubbles um, in that lava than there is actual lava. When this dries, this is an extreme version of vesicular that would be called pumiceous. And so when this rock dries, it's got so much air that it can float in water and can be easily carried by someone. If this was granite, if this was almost any other rock than pumice, you would not be able to just casually be carrying it around on your head. How would you even get it up there in the first place? So this is not a fake rock. It's a real rock, but it is, in fact, pumice. So now we can revisit our magma chemistry chart, which we are also going to go over that chart. We're going to have a good look at that on a Thursday, I'm sorry, when we go over our study guide. But we did all this last week. What we did was we left viscosity and explosivity blank. Do we have enough information now after we've talked about these two things to fill this in? I think we do. But first, we got to get to our rock names. So there's going to be three of them, just like we have three here. Is there an extrusive counterpart of peridotite? There is, but almost no one ever gets to see it, just like no one ever gets to see peridotite. So we're done with ultramafic stuff. It's served its purpose. Its purpose was to say, number one, it's what the mantle's made of, and number two, partial melting of that gives us this. We're not as concerned with it today with extrusive rocks. So you hopefully recall that all three of these phanuritic rocks, all three intrusive rocks, have the similar texture. They have large grains, but they differ in their mineral composition, as you can see, and therefore their color. It's going to be the same with these three rocks. They're all three going to have the same texture, but that texture is different from these. But they are going to have different colors and mineral assemblages because the different mineral assemblages. So a felsic extrusive rock that therefore will have aphanitic texture is called rhyolite. Rhyolite and granite are the same thing as far as their minerals are concerned, as far as their silica content is concerned, as far as their general light color is concerned. They're the same thing. The difference is you can see all the mineral grains in granite, and you can't with rhyolite unless you have some extreme magnification. So same composition, felsic, different texture because of their cooling history. Cooled slowly, large grains, cooled rapidly, small grains. Diorite has an extrusive counterpart, and that is andesite. We were able to talk some about andesite last week. So yes, we do have some andesite that's common on our planet. Andesite, diorite, same composition, different texture. Again, just check textbook page 56 again, where you'll see all six of these compared to each other. And finally, we talked the most last week of all three of these. We talked the most about basalt because we said the oceanic crust is pretty much made of basalt sitting on top of gabbro. Why is basalt on top? Well, because the basalt that comes into contact with the ocean water cools really quickly. So it forms an aphanitic texture. And I don't have them written there. You should probably, I think it's written a little bit later in this slideshow, but you should probably go ahead and write that this is has aphanitic texture, and that has phaneritic texture. Let me one more time emphasize the importance of page 56 in the textbook. All 6 of those rocks appear as photographs on the top of this page. In fact, they are in the same order as there. I've got the phaneritic on top, and I've got the felsic on the left. So make a note to yourself somewhere that page 56 has the 6 main igneous rock photos that show their texture and their color very well. They fit right into this really well. So now what are we going to say about the viscosity of a mafic lava? Mafic lavas have low silica content. So mafic lavas, oh, there they are again from the book. Mafic lavas have low viscosity. They're runny. They're fast. Relatively fast. They're still not fast enough to, they're still not too fast to outrun, but they are relatively fast. Because they have low viscosity, gas escapes easily, and so they erupt in an or non-explosive manner. So it's not going to take a genius to tell what's going to happen over here on the felsic end, right? The higher the silica, the thicker the lava, and therefore these lavas are really, really explosive. But before you jump in and put intermediate here, that would not be accurate. And that's because this amount of silica still results in a pretty thick lava, which means gas pressures can build up to explosive levels. So these are also explosive. They're usually not quite as high magnitude explosive as these, but it turns out on our planet's surface, these lavas are rare and these two are really common. So I think it's more accurate for us to change this to very high and call this high. So this is how I prefer your chart to look. Rhyolitic lavas are not all that common. We don't get to see a lot of these eruptions, and there's not a whole lot of rhyolite deposits on our planet when you compare it to the amount of andesite and basalt on our planet. So these two types of lavas are really, really abundant. These are not. What is really abundant is the intrusive counterpart of rhyolite. And this may just have something to do with the viscosity. A magma that is this viscous may be more likely, because it's moving upward so slowly towards the surface, because it's so slow, thick, slow, it may be more likely, excuse me, to cool off below the surface of the earth than to actually make it to the surface of the earth. Runny lavas, though, are moving much faster, so they're more likely to actually make it to the surface than to cool below the surface. So the 3 most common of these 6 igneous rocks are granite, andesite, and basalt. The 3 most common on our crust are those 3. These can still be found in abundance, but they are really small compared to those to basalt, andesite, and granite. If you don't have your chart filled in like this, then take a screenshot of this particular slide, because this has everything that we need on it as far as felsic versus mafic stuff. And you'll notice that several of the things in our study guide come back to this. All right, so I'm looking at the clock and I see break time. When we come back, we're going to talk more about volcanism, just what a volcano is, and then the types of volcanoes, and then we'll finish up by looking at a few some non-volcanic extrusive landforms. So my clock says 2:25, so no later than 2:40 we will get started in part 2 of chapter 4. See you then.